Okay, next up is Davide Maraschio from the CX team in Italy, and he will talk about enhancing sustainability on NSO using Python.
Thank you, Fabrizio. Hi, everybody. As Fabrizio said, I'm Davide Maraschio from CX, software consulting engineer, and I'm based in Italy, part of a wonderful group of colleagues in Italy. Today, I want to tell you a story of an engineer. We will call her Emma, and the lessons that she learned while struggling with some common mistakes, and also to give you the tools to prevent them. So, first of all, let's start where everything began. That is, of course, our NSO production environment and two packages that Emma developed for configuring L2 VPN and L3 VPN services. The scenario is very simple. The two packages get deployed in the production environment, and NSO starts receiving a northbound service request, and it fulfills this request. So far, so good. The development team is happy, DevOps team is happy, and so our customer. This NSO production environment, like all of them, I hope at least, also this one has an operations team that monitor the platform. At some point in time, the operations team start collecting some KPI related to the platform performances like disk usage, RAM usage, disk usage. And they found out, while analyzing this data, that on the long run, these two packages were silently draining the RAM of the platform. So they alerted our engineer, Emma, and she, of course, started digging deeper in the NSO logs, only to find out that other than the high RAM consumption, there was another problem. Her Python code was taking a lot of time to execute, causing excessive slowness in the service provisioning, so long provisioning time. This gave our engineer some headache, with which probably some of you are already familiar, and start working on this problem. Now, to not lose your attention, let's have some hype. To create some hype, let's see what are the achievements that Emma reached. At the end of the session, we'll see that Emma was able to reduce RAM consumption up to 98% and reducing service execution time up to 80%. Having said that, before guiding you through Emma's journey, let's see what are the checkpoints of this journey. First of all, get to know your tools. We'll see what are the tools that we have in hand and how we can use them. Secondly, we will go through some approaches on how to query the CDB. We will see some design for staged services for performances. For the one who doesn't know about staged service, we will see in a bit. And at the end, we will talk about NSO session lifespan very briefly. Now, tools. First of all, you need to know the tools. In NSO, there are some tools that can be used once you, let's say, activate them. You use the DevTools true keyword to have access to this command. You have access to commands like xpath eval that let you evaluate an xpath expression directly from the NSO CLI. And then the display magic that you can use to display how a CDB node would look like if you want to access it from your Python code. And of course, the logs. In this scenario, Emma used the xpath trace log that should be enabled only in a test environment, since it can slow down the performances in a production environment. Python packages logs and developer logs, the place where NSO trace everything is doing, included like all the steps a transaction goes through. Secondly, build your tool. Emma needed to monitor the package performances. She needed to monitor RAM consumption and execution time. So inside the class performance utilities, she defined a decorator. For the one who doesn't know about the decorator, it's like a wrapper for a function. So when you execute the function, you're actually executing the decorator that will execute your function. Here, Emma used the trace malloc library to calculate RAM consumption, and the time library to take the starting time for the function execution. The decorator executes the function, and after that, it calculates the time taken, which is end time minus starting time. And then with some magic trick with the trace_malloc library, we end up having profile details. In this profile details, we have the function name, the function that we decorated, memory usage, so the amount of RAM used by this function, and the time taken by the function to be executed. And lastly, of course, we print this information inside the Python logs. Now we have the tools, we need to use the tools. So Emma decorated some of her function, and in particular one, get pivot_id. This function here logged an interesting profile. The function is get pivot_id, as I said, and memory usage was 400 megabytes, and time taken for execution was 61 seconds. Looking at the log, she found out that the L2VPN service was taking 62 seconds to execute the Python code inside the create callback, and 67 seconds to execute pre-modification, post-modification callback, and calculating the reverse diff set from NSO. Looking at the L3 package, she also saw that the create here took 61 seconds. But there is also another information. In the L3VPN package, NSO was taking 50 seconds to calculate the reverse diff set and save it into the CDB. Now, as you can see in the L2VPN package, 62 seconds is quite a lot of time, because 61 were just spent in one function. So there should probably room for improvement here. If you're wondering why there is L2VPN service and myVRF service, it's because of staged service. For the one who doesn't know, consider it as part of the L3VPN package, as if it was, let's say, one package. Now, let's get back to the function, the responsible function, get pivot_id. This function here is used to retrieve a pseudo-wire ID given a sub-interface. For example, in this case, the 10gig.e00.3. First of all, let's see what is the path to reach the pseudo-wire ID. In this case, I took an XR device, and the path is very simple. It's config, L2VPN, xconnet group, name of the group, point-to-point, neighbor, and here we have the neighbor IP and the pseudo-wire ID. Now, as I said, we don't know the group, we don't know the point-to-point. We just know the interface. So how was written the function? Using Magic API, and Emma split this path here. She doesn't know the group, she doesn't know the point-to-point, so she just iterate over each xconnet group. She iterate over each point-to-point until iterating over the interfaces, she found the one of interest, 10gig.e00.3. And we stop here. We retrieve the pseudo-wire ID. Here there is next either, just because our service, we already know that the pseudo-wire ID can be found only under one interface, so we stop on the first match. Now, the function, as you saw, it was very simple. It was just querying the CDB, nothing too fancy. So, where is the problem here? What is wrong? Before understanding that, let's see how you can query the CDB. You have two ways of doing that. In your Python code, using Magic API or using xpath queries. xpath queries can be more efficient, 20, 30 times faster than looping over a list, and they use way less memory to execute. This will reduce memory usage and execution time. Why that? Because using the Magic API approach, we have a higher number of context switches happening between the Python VM and the NCS process. And also we have to query and save information in memory. What this means, when I'm iterating over the list of xconnet group and then over the list of point-to-point, every time that in each iteration, I am querying something from the CDB, and I need to save it in memory. So I'm incrementing memory, and also I'm spending time in context switching. So let's see an example. And let's see how Emma solved this problem using xpath queries. We saw the function written with Magic API. Using xpath query, you can use display xpath to see the xpath format of the pseudo-var ID we saw earlier using display magic, and xpath eval to understand if your path is correct or not, to try out on the CLI. And she ended up with this function here. From space reason, this one is splitted in pieces, but you can write it down as a unique string. And it's, as we saw, LCVPN, xconnect, group, point-to-point interface, the name of my interface, which is 10GigE 00.3. Then we step up one level and we go under the neighbor and the pseudo ID. Then we use this function here, xpath eval expr, that is available under a transaction, that takes in input an xpath string, and this one will just return our pseudo ID. As you see, the code is way simpler and it's very quick. As an additional tip, if you know in advance, like we do, that you can find the pseudo ID only under one interface, sub-interface, you can use position, like open close square brackets 1, and it's the same as looping in a list and then stopping on the first match, just to improve a little more the performances. For sake of completeness, this is how you will do it to retrieve a list of nodes instead of a single node. Using Magic API approach here, I took another example, a Juniper device, where I want to collect all the gigabit Ethernet interfaces. You can find them under configuration, interfaces, interface. So we just loop. When we found the one starting with GE, we add that interface in our interfaces array. How we do that using xpath queries? It's very simple. The path is configuration interfaces interface, and here we have a keyword. So interface is a list, and we use the starts with the keyword to say, okay, give me all the interfaces under interface list, which name starts with GE. And then we use the xpath eval method available under a transaction that takes in input the xpath and a function, set interface. This is a callback, and this one is executed every time that there is a match inside that xpath expression. So if I have 2 gigabit Ethernet interface, the set interface method will be called twice. This method here, it's very simple. It always takes 2 parameters in input, the key path and the value. And here I'm interested in the node, so we use the magic getNode method to retrieve my interface and append the interface into the interfaces array. Now, Emma used the xpath queries to implement that function. Now let's see how did this affect the service. The decorator is already telling us that we improved a lot. So memory usage went down from 400 megabytes to less than 1 megabyte, and the time taken went down from 61 to 2.7 seconds, which is quite a lot of gain. Looking at the developer logs, Emma found out that the L2 service was actually okay now, because it was taking 2.8 seconds to execute the Python code inside the create callback, and a total time of 6 seconds to execute all the callbacks and service reverse, calculating the reverse diff set. Looking at the L3 VPN service instead, we actually see a drop in execution time, but we are still getting 35 seconds of execution. And NSO is still consuming 49 seconds to calculate the reverse diff set. So in the L3 VPN service, there probably be room for improvement. Before jumping to the L3 VPN package, probably some of you might be wondering now, so Magic or xpath? The answer is always the same. It depends. It depends because you need to remember that if an xpath query becomes too complex, the API approach may be preferable, especially when the read set is not large, imagine looping in a list that is very small. And to help you decide the best approach, you may do the following. Enable xpath trace, always in the testing environment. And here, this trace logs all the xpath evaluation happening in NSO. It's useful to evaluate the performance of this evaluation and also to validate the results. Then you can use xpath eval command to experiment with your xpath expression. And most important, remember to test your xpath queries and your code on large dataset before deployment, because larger dataset will and may slow down performances. This is very important. Now we can jump to the L3VPN package, and let's see what was going on in that package. The L3VPN package is a staked service. What is staked services? Let's see very briefly. It's an approach, service staking, where services provision other services, and all the services participating in this are called staked. We have two types of services. We have CFS one that configure only services. In this case, it's the L3VPN service, and RFS one that directly configure the devices. In this case, the VRF service. Now, let's have a look on how they were modeled. We are not interested in the L3VPN service. You just need to know that one use a unique ID for each service instance. So every time each user intent, let's say, will be mapped to a single service instance. But let's see how it's done the VRF service. You should be familiar with this. It's a YANG syntax. We defined here the YANG model of our VRF service. And we have a list of my VRF service. And inside, we are using the VRF name as key. And we have a list of devices and a list of interface. So what this model is telling us? He's telling us that there is a one-to-one relationship between a VRF service instance and an L3VPN one. And also that this design leads to an ever-growing diff set for just a single service instance, because a single service instance is going to configure a lot of interfaces and a lot of devices. Bigger diff set means that NSO needs more time to calculate and to save it. And also, if the diff set includes devices that are not part of the user intent, we are wasting both resources and time. What this means? Let's imagine that we already configured one service, that we have the L3VPN service with ID 1 that configured using the VRF service interface 1 on device A. Now, a new service is requested, so user intent. The intent is to configure a new L3VPN service with ID 2 that will configure interface 2 on device B using the same VRF service, because both service ID 1 and 2 share the same VRF name. Now what's happening? Here, both the configuration are part of the same diff set. So NSO, when you configure ID2, needs to calculate the diff set for either the device A and device B. And this takes time. So how this can be redesigned? There are a few ideas that Emma come out. One of them is assign a unique ID to the service instance and move the device list inside a container and the interface inside a leaf. Here we drastically reduce the scope of the service instance, because here the service instance is taking care of configuring just one interface under the VRF. Another way of doing that is moving, for example, the service point. You might be move the service point under the list of device and keeping the VRF name as a key. In this case, we partially reduce the scope of this service instance because we still have a one-to-N relationship, but N is limited to only a list of interfaces and one device. And also it might be useful because you, from the CLI, you might want to know what are the services configured under a VRF, and you can still do a show of your VRF name of your VRF and see all the services configured under it. Now, how did this design affect the services? What we said is that the new service redesign will reduce the scope of each service instance, limiting the diff set size. And this impacted the L3VPN service in this way. The create callback execution time dropped down from 35 seconds to 2 seconds, and NSO took only 17 seconds respect to the 49 to calculate the reverse diff set and to save it. You might be wondering, but okay, if I reduce the scope and I'm limiting the diff set size, why also my Python code took less time to execute? Well, the answer is very simple. Depends on your Python code, but you need to apply a template for each interface, for each device. You might be needed to read the part of the configuration on the device for each interface, and that takes time. So this solution here reduces not only the reverse diff set calculation, but also the time to execute my callback. Now, Emma is happy. She solved the problem on both packages, L3VPN and L2VPN. And we can move on and teleport our engineer to the NSO sessions land. Today, we talked about resource wasting. Resource wasting is not always obvious, and sometimes is hidden in small details like session and transaction lifespan. As you should already know, any read or write operations done in NSO is associated with a transaction and a session. And for a single session, you can have more transactions opened. You also have available some high-level API, the Magic API, like start read trans and start write trans, that might give you the idea that opening and closing transaction is priceless. You can do it whenever you want. But it's not really like this. Sometimes it might be more efficient to have a long-running transaction and reuse it, even if a prolonged use might lead to an increment in memory usage because you keep a transaction opened for too long. So there is a trade-off that the developer must understand between code complexity, because if you keep a transaction open, it means that you have an object that you need to move around your code. But on the other hand, it's not best practice to open and close transaction all the time. So what's the better approach? Again, the answer is it depends. It depends, but we have some key points to keep in mind. First of all, open a transaction toward the right database. If you're reading operational data, open a transaction towards an operational database. Choose the right operation. If you are reading data, do not open a transaction for read-write, just opening for reading. And third, as I said, avoid to open and close a transaction multiple times in the same callback. As a last tip, in the action, there is a valid usable transaction that is available that I see not many are using it, but it's there. It's a read-only transaction, but it's still there and can be used. You just need to adding it as an input parameter inside the action callback. Now, Sun is set in the NSO sessions land and also for this session. I want to leave you with some references, a best practice guide that is published in the Crosswork Automation Hub, and some links about staged services and common troubleshooting steps that you might find useful. And that was it for the presentation.
Thank you, Dan.
Perfect. Okay, thank you.